In this video, I want to walk through the mechanism for triacylglycerol hydrolysis. And before we dive into the mechanism, let's just decipher those words a little bit. So the fat that you eat, the triglycerides in the fat that you eat, are made up of a few pieces. One piece, this sort of bookshelf, is glycerol. And you have sort of 3 shelves on it. And on each of those shelves, you can put a sort of fatty acid book. So you have glycerol as a sort of backbone, and then 3 fatty acids, 1, 2, and 3, that you can store there. Now, each of these fatty acids has a group called an acyl group, and the acyl group is really just a carbon double bonded to an oxygen. So you have 3 of these acyl groups, triacyl. They're sticking onto glycerol, and so glycerol. The way they do that involves removing water. That's a different reaction than we're going to discuss at length here. Oops. But ultimately, you remove 2 H's and an O, so water, and each of these fatty acids attaches to the glycerol. So you're left with 3 acyl groups on a glycerol, so that's triacylglycerol. And this is the fat, the triglycerides. Triglyceride is synonymous with triacylglycerol. That's the fat that you ingest in your food. So you ingest fat in your food, it goes into your small intestines, and it looks like this. But this is a very big molecule, and it's also very insoluble. It's very nonpolar, and so your small intestines is watery, and so this will glob up, and it's hard to digest that way. At first, your body breaks it up, the big fat glob, into smaller pieces using bile salts, which act a lot like soaps that allow fats to mix with water. But then, to break it into even smaller pieces, your body removes 2 of these acyl groups, the one on top and the one on the bottom. It does that using water, and that is the mechanism that we're going to explore here. So we're going to explore how your body breaks down the individual molecule into smaller pieces so that it can pass through the cell, the mucosa, into the mucosa of your duodenum, so into your cells from your digestive tract. Okay, so we have triacylglycerol, that's this molecule here all together, and then we're going to be breaking it apart. That's what this lysis means, breaking it apart using water, hydro. Ultimately, that's going to be through 2 what are called nucleophilic acyl substitution reactions. So nucleophilic acyl substitution. So an acyl group, remember, is carbon double bonded to oxygen. Sometimes you can have a leaving group attached to that carbon, and you can do a reaction where the leaving group gets replaced with a nucleophile. So it involves a nucleophile, so it's nucleophilic. You have that acyl group, and one thing, the leaving group, is getting replaced by another, so it's a substitution reaction. Okay, so this this triacylglycerol hydrolysis is going to happen through 2 nucleophilic acyl substitution reactions. The enzyme that we're going to use is pancreatic lipase. It has 449 amino acids, and here there are several amino acids. They have the numbers here for where they occur in the chain. So this serine here is the 152nd amino acid, aspartate here is the 176th, and histidine is the 263rd in the long chain of amino acids that make up this protein enzyme. And when the protein folds, although these are on different points in the chain, once they fold, they're all close together in the active site. So these are the amino acid R groups that are going to catalyze this reaction, where we're going to break this top and bottom fatty acid off of the triacylglycerol. Ultimately, our nucleophile is going to be the oxygen on this serine here. Now right now it's only slightly negative, So it's a weak nucleophile, but it is going to attack the carbonyl carbon, that's the carbon double bonded to the oxygen, of these triacylglycerols. This is an electrophile. It's losing electron density to the oxygens. The oxygens are very electronegative, so they pull electrons to themselves, and whatever they're bonded to loses those. That is especially true for this carbonyl carbon there. So this is going to be our electrophile. In addition to it being pretty slightly positive, there's also a pi bond here, and those are easier to break than sigma bonds. Remember, the sigma bond is the first bond you ever form. Every bond after that is a pi bond. Pi bonds are weaker than sigma bonds. So this is a very good electrophile. It's a target that a nucleophile would want to attack because it has a bond that will break easily, and it's pretty slightly positive. To make the reaction go faster, though, we need the serine to be a stronger nucleophile. Right now it's a weak nucleophile because it only has a slightly negative charge. So to give it a full negative charge, we're going to do a proton transfer. We're going to move an H+ from the serine to another place in the enzyme, in the active site of the enzyme. Now ultimately, it's going to be this lone pair on the histidine, so this is histidine, this lone pair is going to move over and push these pi electrons here to act as a base and steal that hydrogen. And that will push these electrons onto the serine and give it a full negative charge. So after this first step, what we'll have is those pi electrons will now be a bond to this hydrogen, so that will have moved. Those bonding electrons will become a lone pair. This oxygen now has a full negative charge, so it's a strong nucleophile. And this lone pair of the nitrogen becomes a pi bond. Now notice this nitrogen is now has 4 bonds, and therefore it has a full positive charge. That's stabilized by an aspartate nearby in the active site. On the chain, the aspartate is amino acid 176, but when the protein folds up into the enzyme, it's pretty close to the histidine, and the negative charge at the end of this aspartate stabilizes the positive charge that forms in the histidine. So now our serine is a strong nucleophile, and it can finally attack this outermost, less protected carbonyl carbon. So this nucleophile can swoop in to attack the carbonyl carbon. The weakest bond, the pi bond, breaks. Now note that this oxygen has 2 lone pairs right now. So after this next reaction, let me just make some room. So after this next reaction, this bond will become a 3rd lone pair. This oxygen will have a full negative charge. This lone pair will become a bond, and that will make the negative charge go away. So I'm going to draw a bond there. And that accomplishes that. Okay, so now we have our tetrahedral intermediate. You might remember from nucleophilic acyl substitution reactions, the nucleophile attacks, breaks the pi bond, and you get this tetrahedral intermediate, because this carbon here is bonded to 4 atoms, single bonded to 4 atoms, so it's sp3 hybridized and tetrahedral. But the oxygen on top, swinging around with that negative charge, is very unstable, and the carbon next to it has this pretty positive charge still. It's bonded to 1, 2, 3 oxygens all of them pulling its electron density away. And so it attracts this negatively charged oxygen a lot. And these electrons can snap back down because it's attracted to the positive charge there. Now, when it does that, it's going to expel a leaving group. And the leaving group is going to be, and I'll highlight it in green, it's going to be the rest of this molecule, this gigantic leaving group. But really, the part that's doing the leaving is this oxygen here. That oxygen would be a bad leaving group all by itself because it would have a negative charge. But to stabilize that negative charge, it steals this hydrogen back. That pushes these electrons back, and then these electrons become a lone pair again to stabilize the positive charge on this nitrogen. So, after this step, this negative charge will go away because the lone pair is not just going to be on the oxygen, it's going to be a pi bond again, actually. And then this bond will break this whole group here. Oops. This whole group here will leave, and this oxygen stole this hydrogen. Oops. From the histidine. So that becomes our pi bond. This pi bond moves, becomes a lone pair on that nitrogen. Okay, so what we've done was a nucleophilic acyl substitution. If you think about it in these terms here, we had a leaving group and we replaced it with a nucleophile. We had a leaving group on a carbonyl carbon, we replaced it with a nucleophile. What we started with ultimately, our leaving group, didn't look like it at first, but this whole thing was our leaving group. And ultimately we replaced that with a nucleophile, which was the oxygen of the serine. And ultimately, and through that, the whole enzyme. So we replaced one gigantic thing with another, a leaving group with a nucleophile. That's a nucleophilic acyl substitution. And notice we've removed one of the fatty acids from the triacylglycerol. That's the whole point of this reaction, is to break the triacylglycerol into smaller pieces so that they can move through the cell membranes of the cells in your small intestine into the mucosa of your duodenum. Okay. Well, we're not quite done yet, because this needs to become a free fatty acid, so we need to detach it from this pancreatic lipase enzyme, and we're going to do that through the same exact type of reaction that we just did. We're going to do that through another nucleophilic acyl substitution, but now it's going to be the enzyme that's the leaving group, and the nucleophile that's going to switch places with it is going to be an OH from water. And so this is the hydro of the hydrolysis part. It's a hydrolysis reaction because we're breaking this apart, lysis, and it involves water, so it's hydrolysis. Okay, well, just like before, this oxygen is not a strong nucleophile. It only has a slightly negative charge. Slightly negative charge, just like the oxygen of the serine before. So to make it a better nucleophile, we have to give it a full negative charge. And we can do that just like before with a proton transfer. So just like before, this histidine can do that proton transfer. This lone pair can move over, push these electrons to become a base, that steal one of these hydrogens. And the electrons snap back onto the oxygen. So, after that step, let's move down here. So after this step, this lone pair will become a pi bond. This pi bond becomes a bond to this hydrogen here. And this bond becomes a third lone pair on the water, oxygen, giving it a full negative charge. And now we have a strong nucleophile. So we did that proton transfer to rev up that nucleophile, make it a stronger nucleophile. Okay, now, remember conceptually, the enzyme is now the leaving group in this nucleophilic acyl substitution reaction, and the hydroxide ion is going to be our nucleophile. So the nucleophile will swoop in, attack the carbonyl carbon, the weakest bond, that's the pi bond, breaks, and the electrons go onto the oxygen above that. So, after that step, we will be left with this pi bond breaking. Now we have a third lone pair here and a full negative charge on that oxygen. This lone pair becomes a bond, and actually, well, yeah, okay. That lone pair becomes a bond. And so the negative charge on the oxygen goes away because the electrons that were giving rise to it are now being shared. Okay, so here's our tetrahedral intermediate in the nucleophilic acyl substitution. But this negatively charged oxygen is swinging around, and it's really attracted to the slightly positive carbon of the tetrahedral intermediate. This carbon has a significantly positive charge because it's bonded to 1, 2, 3 oxygens with negative charges. So, oops. So, it snaps back down to try to form a bond with it and kicks the best leaving group off. And the best leaving group is going to be the serine oxygen. This is our leaving group now. That would be a bad leaving group all by itself because it would have a negative charge. But to stabilize that, just like before, it steals the hydrogen back from the histidine. The electrons to that form a pi bond again, and then the nitrogen gets its lone pair back. And one thing I forgot to emphasize there is when that formed that bond there, that nitrogen had a positive charge, right? This nitrogen here has 4 bonds, so it would have a full positive charge, and that's being stabilized by the aspartate on position 176 in the amino acid chain. So, at this point, we get our free fatty acid. So this lone pair becomes a pi bond. This bond breaks, becomes a lone pair. The other lone pair steals this hydrogen. The other bond becomes another pi bond. And this pi bond here becomes a lone pair on the nitrogen, relieving it of that negative charge it had. And so ultimately what we have here is a fatty acid. Let me redraw this so it looks a little less awkward. I'm just going to make that bond go there, and then I'll have the OH bonded to it. And so notice that's a fatty acid. You have a non-polar part, the fatty part, and a carboxylic acid, so fatty acid. So we have a free fatty acid, a free fatty acid here. That same exact process happens again to the bottom fatty acid of our original triacylglycerol. So ultimately, using this pancreatic lipase enzyme, we were able to do 2 nucleophilic acyl substitutions to remove a fatty acid from what was a triacylglycerol. Now the whole process is going to happen again for the fatty acid on the bottom. And after that happens, and it attacks the top and the bottom because those are the most exposed, after that happens, the pieces are small enough to travel through the membranes, the cellular membranes, into your cells from your digestive tract, where new epic journeys await them. So if you understood that process, you can stop here. Just for the sake of completeness, I'm going to repeat that process for the fatty acid chain at the bottom, the second one here. So 2 nucleophilic acyl substitutions. First, this serine is a poor nucleophile. We need to turn it into a better nucleophile. So these electrons move over and push these electrons to steal that hydrogen, which then, the electrons in that other bond, snap back onto the oxygen of the serine to give it a full negative charge. So in that first step, we just activate this enzyme. That lone pair becomes a pi bond, pushes these pi electrons to attack this hydrogen. So this nitrogen is now bonded to that hydrogen. The electrons in the bond go back onto the other oxygen, gives it a full negative charge. So now that's a strong nucleophile. And notice that this nitrogen over here has 4 bonds, so it has a full positive charge now. So now that we have a strong nucleophile in our serine that can attack the carbonyl carbon there, which is slightly positive because of all those bonds to oxygens. The weakest bond breaks, that's the pi bond. The electrons snap back onto that oxygen there. So that gives us our tetrahedral intermediate. So that becomes a third lone pair on this oxygen, which has a full negative charge. And now the serine from the pancreatic lipase is attached to that oxygen. Oops, I'm sorry, to that carbonyl carbon. So this is going to be a long bond. Actually, let me see if I can rotate this just a little bit. There we go. So that's our tetrahedral intermediate. This oxygen, very unstable. It snaps back down and kicks off the best leaving group. Oops. Snaps back down to this to create a bond there, and the rest of this molecule is going to be the leaving group. So the leaving group is all of this here. Now, as it is, it's not the best leaving group because the oxygen that would be doing the leaving would have a negative charge. So to stabilize that, that oxygen ends up stealing the hydrogen back and creating that whole cascade. Okay, so now this hydrogen ends up going onto this oxygen, and this whole thing is going to be a leaving group. Let's just do this. So So that whole thing is a leaving group. And now we have a piece that's small, another piece that's small enough to go through the mucosa. This lone pair becomes a pi bond, and so we've done a nucleophilic acyl substitution. Our leaving group here and our nucleophilic enzyme. So we've removed the fatty acid from the triacylglycerol, and now we have it attached to the enzyme. So now we just need to remove it from the enzyme and attach it to an OH to turn it into a fatty acid again. So we're going to do another nucleophilic acyl substitution, but this time the nucleophile is going to be the oxygen from water. That oxygen is not the best nucleophile right now, it's only slightly negative, so we are going to do a proton transfer to make it a better nucleophile. Oh, and let me finish this up from last time first. So here, this bond becomes a pi bond. This pi bond goes onto the nitrogen and becomes the lone pair again. Okay, so we're going to make this nucleophile a better nucleophile. We're going to do that the same way we did before. The lone pair moves over. That pushes these pi electrons to attack. They attack the hydrogen. Oops. And the electrons in the bond snap back onto that oxygen there. So this lone pair becomes a pi bond. This pi bond becomes a bond to that hydrogen. And that bond becomes a lone pair on the oxygen, which now doesn't have a partial negative charge, but a full negative charge, so it's a strong nucleophile. And now we're ready to do our nucleophilic acyl substitution. This nucleophile can attack that carbonyl carbon, push the pi bond up, the pi electrons up, and that'll give us our tetrahedral intermediate. So this lone pair won't exist there anymore. It'll be a bond, and that bond is going to go to that carbonyl carbon there. This pi bond is going to break, and the electrons are going to go onto this oxygen, giving that a full negative charge. Okay, so we have our tetrahedral intermediate for our second nucleophilic acyl substitution. And our leaving group again is going to be our enzyme. This whole thing is going to be our leaving group. So what'll happen is this really reactive oxygen there with the full negative charge attracted to that carbon, the lone pairs swoop back down, recreate the pi bond, and kick off the best leaving group. The best leaving group is going to be the enzyme, because if these leave, this oxygen can steal that hydrogen, and the electrons can move over to stabilize the positive charge that has been on that nitrogen there. And I might have neglected to put that there, but that nitrogen has 4 bonds, so it would have a positive charge there. All right, so at that point, this lone pair will become a pi bond. Because the electrons are being shared, they're not going to give that oxygen a full negative charge. This bond will break, it's getting pushed off, and our leaving group is going to leave. Now, when it does, the bond that just broke is going to become a lone pair, and the lone pair on the opposite side is going to steal this hydrogen. So that's stable. The electrons in the bond to the hydrogen will become a pi bond, and they'll push these pi electrons over to stabilize the positive charge on that nitrogen. So we're left with our neutral pancreatic lipase enzyme again. And let me draw this so that it looks a little less awkward. I'm just going to draw that OH on the other side. And so that gives us another free fatty acid. So overall, the action of this pancreatic lipase enzyme has given us 3 products. We have this fatty acid here that we just made. We have the monoacylglycerol here. And if we go up even more, we have the first fatty acid that we released. So the pancreatic lipase enzyme breaks what was a triglyceride into 3 things: a fatty acid, a second fatty acid, and a monoacyl, because only one acyl group on this glycerol. Those pieces are now small enough to travel through the plasma membranes of the cells that line your digestive tract into your body, into the mucosa of your duodenum, where they have new journeys await them. But so far, what we did in this video was we walked through the nucleophilic acyl substitutions that give you triacylglycerol hydrolysis.